this thin rod, a line of charge. Let's say our rod has a total length L. And let's say we want to find the electric field at a point right here along the line of the rod. Some distance A away from it. This rod has a total charge, we'll just call it big Q. We'll say it's positive. So we want to find the electric field at a point along the axis of the rod, distance A away. Now there's nothing at this point. Okay? This is just a point in space that we're interested in. I am going to draw a coordinate system. So our rod lies along the x-axis. And the point we're interested in is at the origin. We're going to need some reference points. That's why I'm drawing a coordinate system. Now, the only equation we know of right now is this one. This is certainly not a point charge. This has a whole bunch of little charges on it. We can, though, treat these as a whole bunch of little tiny point charges. All of these charges are contributing to the electric field over here. First of all, what direction will the electric field be in? The left, away from the rod. Each piece of the rod is contributing to the electric field over there. But do they all contribute? Do each of these little positive charges contribute equally? Why not? They're different distances away. Exactly right. According to this equation, for a point charge, the electric field depends upon not only the charge itself, but how far away we are. Each of these little pieces of charge are a different distance away. You will have to integrate, yes. So for example, let's call this dq, the amount of charge on this little infinitesimally small piece. It's a point charge that way. The strength of its electric field will depend upon how far away it is. Okay. So this is some distance x away. If I choose a piece down here, it also has dq. But its distance away, we can still call x, but it's not the same x as the other one. They're different distances. So simply what we're going to do is we're going to treat this as a whole bunch of little teeny tiny point charges, and we're going to sum up their contributions to the electric field to get an overall electric field. The summation of a whole bunch of infinitesimally small pieces is simply the integral. We can say the electric field is the integral of all of our little dq's, each little infinitesimally small piece of charge, over how far away they are squared, our half. So same equation, instead of calling it big Q, meaning the total charge overall, we're saying dq, and we're summing each of them. So what we need to do, since r, in this case, is x, and that is what is changing, we need to write dq in terms of a dx. If you know the variable is changing, in this case, the variable that's changing is x. You can't integrate x with respect to q. That's not valid. If you want to have x be your variable, you need to have a dx in there in order to integrate. So we need to figure out what dq is in terms of dx. R, we already know is x. It's however far from the origin to the point we're interested in. Our hat, this piece, we already know, because we already know the direction. The direction's going to be negative I hat. So we already know that. We're good. So the piece we need is dq. We have to have everything in terms, everything that's changing in terms of the same variable. So dq, we actually can relate to the length of this. The length of this is called dx. That's what we mean by dx, the length of that little tiny piece. We can relate the two by way of the linear charge density. We know lambda is total charge over total length. But if we pulled out that little teeny tiny chunk, we haven't changed the density. It's the same thing as the amount of charge on that little chunk, which would be dq, over the length of that little chunk, which would be dx. The ratio is the same, whether I look at the whole rod or a piece of the rod. So using this relationship, we can solve for dq. If we bring dx up, we can say dq is equal to q over L times dx. Or if you want to write it in terms of lambda, you can say dq is equal to lambda dx. They're equivalent. Okay, those are the same thing. I'm going to write it as q over L dx because we said we had a total charge q and length L. So I'm going to write it in terms of those. So once you know what each of those little individual pieces are, we simply need to plug them in. dq, we just said, was q over L dx. R is x, so x squared is in the denominator. R hat is negative I hat. We need one more piece of information. We need limits on our integral. The limits of our integral tell us, or tell the function, where the charge is physically located, where it is. Because we're integrating along the x-axis. That's what it means to integrate with respect to dx. So we're integrating along the x-axis. We need to tell the function where to integrate from. We don't want to integrate the whole x-axis from 0 to infinity because we don't have charge from 0 to infinity. Where is our charge physically located? Where does it start? At A. So our lower limit is A. Exactly. It ends down here at A plus L. So those are our limits. Our limits tell us where the charge is physically located. So, as with any other integral you've ever done, you pull out the constants. The KE will come out. The Q over L, those are constants, so they'll come out. The negative I hat will come out. I'll just put the negative sign in front. That leaves us with 1 over x squared dx from A to A plus L. What's the integral of 1 over x squared? Negative 1 over x. 1 over x squared is the same thing as x to the negative 2. So our integral will be negative 1 over x. We need to plug in our limits. The negative signs are going to cancel. So we'll get KE Q over L I hat times plugging in the upper limit 1 over A plus L minus plugging in the lower limit 1 over A. This is our electric field at that point. We would simply need to know values to get a numerical answer. We will come up with a negative value because 1 over A plus L is smaller than 1 over A. So when we actually do this calculation, you'll get a negative value, which is good because we need to come up with a negative answer since the electric field points to the left in the negative direction. This equation will work anywhere along the line, along the axis of the rod, or of a rod. questions on getting any part of it? I
So
do,
maybe that was out in front, you just distributed through.
I canceled it because the negative times the negative will give me a positive. That's why I got rid of it. Mathematically, it will come back if you had numbers to plug in. You'll get a negative sign back, which is good. It will represent the fields in the negative direction. What would be different from a point A on that side and a point A on this side? Yeah, just the sign. We'd have a positive I hat. The negative signs would not have canceled. We'd still have a negative sign in the equation, but a negative times this term will be negative, will give us a positive answer. So the electric field along the line of the rod is that way. Is that equation going to be valid if we want to know the electric field up, say up there? No. Some of these change. Okay. We'll do that one tomorrow because we certainly don't have enough time to do it right now. But as a forewarning, I do expect you to know how to at least set these up, if not solve them. Okay? So you will want to get a little practice with them. There's only so many you can do, really. You can have the rod here, or you can have the rod here. I'm not going to make it three-dimensional and make it stick out. Okay? I'm also not going to require you to integrate over a surface area or throughout a volume. So no two-dimensional or three-dimensional integrals. As far as integration, I'm going to have you just do rods. Okay. Turns out, for charge distributed over a surface or throughout a volume, there's another way in some situations to find the electric field that does not require integration. We'll be talking about that in the next chapter. So it tends to be a little easier than integration anyway. So we don't have to integrate, we won't. But finite length rods, you do have to integrate. So tomorrow we'll do the example where we put the point we're interested in somewhere else, not along the axis.